thanks everybody for coming. I'm very excited for this week and for this workshop in general, and I'm very grateful for all of you being here. For this talk, what I really want to do is motivate and situate the research collaboration that we're putting together within the context of the history of mechanistic interpretability for AI safety as it's developed so far. But before getting into that, it's a little bit about us. So Principles Intelligence, or Princeton for short, we're an AI safety field building organization that's focused on supporting interdisciplinary collaborations aiming at high assurance safety guarantees for strong AI systems. We do a number of different things, but maybe for this audience, what's most relevant is that we support research collaborations such as these by running multiple workshops. We do internal research, and we also help incubate and sponsor new academic labs and research organizations that want to work on these agendas. So if you're interested in getting involved, please come talk to either I or Lauren at some point this week. But over the last year, we've been building this collaboration that's at the intersection of statistical physics, deep learning theory, and AI safety, which we're now branding as Physics-Inspired Ambitious Mechanistic Interpretability, or PIAMI for short. And this talk will be just contextualizing this research agenda and the history of mechanistic interpretability. But we have a research division. These are some of the faces of the technical staff there. We also have many wonderful operational staff, many of whom, without whom none of this could happen. And we also, act as incubator, we grantor, and fiscal sponsor. And these are some of the organizations that we've supported thus far. So an outline for the talk is just mechanistic interpretability, the case for PIAMI, and how folks can get further involved. But maybe before getting to this, let's just go over just a primer on AI safety risks, and maybe the beginnings of the field that we now know as AI safety. Arguably, people have been worried about AI takeover since the beginning of computers, right? There's like these quotes by Turing and von Neumann that people like to spot out that I, at this moment in time, can't recall. And even arguably, Frankenstein can be read as like an AI takeover kind of story. But the field didn't really coalesce into a institutional shape with a unified research agenda, not until like the 2000s, when organizations such as MIRI or Future for Humanity Institute kind of came together and started really conceptualizing these risks. So in 2014, Nick Bostrom published Superintelligence, which laid out, I think this was the first academic publication that really laid out a case for AI risk, catastrophic AI risk, which was founded on 4 different premises. 1, orthogonality thesis. It's because you're smart, doesn't mean you're nice. Instrumental convergence. Doesn't matter what you're doing. There's a certain set of strategies that will help you get there, such as being more powerful, self-preservation, et cetera, et cetera. Anti-naturalness of human values. So, human values are just kind of a evolutionary accident that we developed. By default, we shouldn't expect other things to attain human values. And good Hart's law. So, when a measure becomes a target, it ceases to be a good measure. So the general idea is that, if you build an AI system, you try to give it human values, it's going to learn some proxy to this. And this proxy, by default, is going to be cursed with all the different horrible things that happen with instrumental convergence, such as power seeking, deception, et cetera, et cetera. And once this AI system is much more stronger than you and is nearly optimizing for this proxy will now become uncorrelated with what you actually care about. And the general kind of doom takeoff story that they told is that you have this misspecified objective. The AI realizes it's misaligned, but not powerful enough to take over, tends to be aligned, gains more power, gains a slight strategic advantage over humanity. And like all this, seems, perhaps like science fiction, especially in the 2000s. But unfortunately, like now, we more and more live in a world where some of these components of these risks are becoming things that we see actually in the real world, right? There's misspecified objectives with reward hacking, models that develop evil awareness and have tendency for self-preservation behavior, and they're becoming increasingly more powerful and increasingly shorter timescales. So what is to be done? So I claim, and other people I think earlier on in the field really lay out 4 desired for a solution for this particular problem. So one, we want to be able to reason about the safety properties of learned policies prior to deployment. If we deploy them, they might be deceptive, they might be too late. We want to have high confidence over assessment of these safety properties. Could go very wrong if we don't. We want this to be robust to distribution shifts in the deployment setting, because we expect the deployment setting to shift. And our methods should be scalable to future, more capable systems, because we expect the progress of AI to become quicker and quicker. And this really lined up with a lot of the inspirations that many AI safety researchers who were first going into mechanistic interpretability had. They wanted to use mechanistic interpretability to catch problems with auditing, deliberately design architectures which were more interpretable, have better informed oversight over these training processes, and maybe perhaps instead of building agentic AI, we can use them as microscopes to better investigate natural phenomena. So let's dive into the history of mech-interp. But before I go into this, so much of this history is laid out in a blog post by Lee Sharkey called Mechanistic Interpretability Has Never Been Pre-Paradigmatic. I take issue with the term paradigmatic, so I'll try not to use it. But also inspired by some talks that Logan has given in the past. And also, this is not aimed to be a comprehensive survey. I'm mostly detailing the trajectory of the research agenda led by Chris Olah, which has started OpenAI's Clarity team and now at Anthropic, mostly because this has been a very dominant voice in the field. And also because they really kind of set the stage for how these tools will be used and applied in the deployment settings. So first wave of mech-interp, 2012, 2021, we have a research culture that is really built around this idea that neurons are the fundamental unit of computation inside of neural networks. There's some initial skepticism in the field that there can be anything, the neural networks aren't anything resembling kind of a deductive process. There's just this bag of heuristics that kind of magically happens, but lo and behold, some early interpretability researchers were able to find pretty interpretable structure. So what do they do? So this is these curves here, they're a picture of early neurons within inception V1. And how these visualizations came to be is that you would pick a neuron, and then you do some kind of optimization process over the input space so as to maximally activate this neuron. And you get these pictures, and this is further corroborated by a set of controls and ablations on the right. But not only do you have these early curves, as you move further and further down the layer, you see that these curves, progressively compose to produce more and more complicated structures, such that by the end, in one of the final layers, you have something like this, some pretty sophisticated structure, which is like this multi-dimensional dog that's always looking at you, no matter what way you look at it from. And this kind of set the stage for conceptualizing mechanistic interpretability in terms of traditional software reverse engineering, where the neurons were variables and they get updated as activations propagate through the network. But there was a problem, which was this issue of polysemantic neurons. So some neurons just didn't seem to have multiple interpretations. There's this somehow a cat and a car and cat legs at the same time, which really posed some issues to this idea that you have as many variables as you have neurons. would seem to imply that your network can and does learn to represent more variables than neurons. And then, which gave birth to the second wave in mechanistic interpretability, which is built around trying to accommodate for this anomaly. So yeah, they borrowed some insights from compressed sensing and realized that, well, if you have representations which are actually sparse, they don't have high co-occurrence, you can actually represent them pretty well. And the new kind of mental model for what's happening inside of neural networks is that you have this dense network that's actually noisily simulating this much sparser, much larger disentangled model, which is monosemantic. And after this theoretical insights came some engineering breakthroughs. So yeah, I guess directly inspired by this was the utilization of sparse dictionary learning, which is autoencoder whose dimension is larger, inner or hidden dimension is larger than the input, and you train on some sparsity constraint. Use this for interpreting neural networks. And lo and behold, we got interpretable structure. For large part, these neurons seem to be monosemantic. And yeah, you could use them, you could stimulate them and get predictive results, such as in this Golden Gate Bridge example. And this was great. People were very excited. There was a declaration of victory. There was this idea, this kind of conception that perhaps there was no more fundamental breakthroughs to be made in interpretability. That really it's largely just an engineering problem. We just have to have better and better sparse autoencoders. And much of the progress between 2023 to 2025 in mechanistic interpretability has actually been around this, is an engineering culture which creates novel benchmarks and hill climbs on these benchmarks by making slight architectural adjustments in sparse autoencoders to make them better. But of course, unfortunately, there's a few anomalies with these. And upon closer inspection, it did not seem like these were actually capturing atomic units of computation inside neural networks. First example of this is feature splitting. You could just make the sparse autoencoder wider, and you have more and more features. Splitting the atom, this doesn't seem right. Other ideas, feature absorption. Yeah, unfortunately, if you have some if you have two neurons or two concepts which are actually supposed to have high co-occurrence, which would be in the case of any kind of hierarchical structure, the sparsity penalty actually incentivizes the sparse dictionary to kind of combine them into one latent as opposed to having them be separate. And additionally, there was many phenomena which we started to observe that lied outside of the superposition hypothesis. Mainly, this notion of feature geometry. There seemed to be more rich structure within the geometry of these latents. Nonlinear representations are not addressed by this superposition hypothesis, and neither are representations which are distributed across neurons, which is what we would expect in a mechanism such as attention. And what's novel about this crisis anomaly period is that there's been a trend in trend's the right word, but there's been a movement in the field who's, I guess, pretty pessimistic about the original vision for mechanistic interpretability. And they've updated not so much on our current tools and understanding are insufficient, but the whole project at large is just doomed. And no amount of science will undo that. And primarily, a lot of this work is, I think they're driven more by having direct applications with these methods, which they believe will not be fundamentally improved upon, and apply them to real-world scenarios. Which, to be fair, I don't want to demonize. It's very, very important. The fact that we have production-ready probes that are being used at this moment to make systems that are currently being deployed safer is really wonderful. And this is a good methodology to take. But I think yeah, I'm of the opinion that there is much more fundamental research that can be done, and we can still do, still solve ambitious mech-interp. But before we get into that, maybe just to sum things up a bit. So I think in my assessment, the reason why SAE is faulty is because they're based on incomplete data model. So they were designed to account for one specific property, which we expect to be present in the latents of natural data, which is sparsity, and optimizing just for finding this without consideration of other properties which we expect to find in natural data, we get compromised, and we get issues such as feature absorption. Really, in the theoretical side of things, the field is still confused about what a feature is, about what its atomic unit of computation should be. These are largely remnants of empirical findings, and there's no real theoretical basis in first principles account. I mean, there's sparse work, but there's no really rich theoretical account which interfaces with either architecture design or unsupervised feature extraction. Some of the field is turning away from the scientific challenge. So some reasons for hope, maybe just to state the obvious, is that this kind of iteration is typical in science. We have provisional theories and accounts for things, and we iterate and refine them as we go along. But also maybe I want to address often a methodological reason for pessimism is that there's no ground truth, right? This is often discussed in mechanistic interpretability. There's no real ground truth for these latents, and this is a really hard problem. But this isn't an unprecedented problem. I claim that this happens in science whenever you're trying to do any kind of conceptual innovation. And if you haven't read this book, I love this book. You should definitely read it. It's Inventing Temperature by Hae-Sok Chang. And he looks at the history of thermodynamics and temperature and thermometry and how they kind of inform one another. And the basic problem is how do you define temperature without being able to measure it? But how do you measure it without having a definition for it? The answer is you have a really close interplay in the research cultures between measurement device creation and theoretical development, and they mutually build upon each other in a way that coheres to the same picture as opposed to being foundational to one of them. And I want to claim that, for making an analogy to the history of mechanistic interpretability, to the history of thermodynamics, that we're somewhat at a Thomson moment, where, in the 1840s, in the history of thermometry, they had people could create gas thermometers, but they gave slightly different readings depending on which particular gas the thermometer was based on. And unfortunately, there was no real way to empirically distinguish these two things, which one was actually giving the right temperature reading, because there was no temperature standard. But a breakthrough came in when Thomson actually came to define temperature in terms of Carnot efficiency, rather than at the moment in time what was thought to be a physical substance, the caloric, and was able to replace the question of which is the correct gas to be using for measuring temperature, which was the question of which gas most closely approximates ideal behavior as laid out in the Carnot's engine. And I think this is maybe the target another reason for hope is we have a target to shoot for. So I think this research collaboration and the kinds of research we really want to be building and supporting aims to develop a full account of how intrinsic representations in structured data interacts with the architectural biases of neural networks across training time to embed different representations and algorithms inside of the learning components of an AI system. And we also aim to have a much closer interaction between theory and measurement development than has in the past. I think there is, the big motivation for having this kind of workshops is that there is a rich academic tradition that has been studying the theoretical side of these neural networks. That's just, for sociological reasons, not in conversation with people who are leading the engineering efforts. And we also believe that, for, technical reasons that I won't get into, that, these can get, there's hope for these tools, physics-inspired tools, to account for worst-case guarantees in neural networks. And like I said, the main problem is sociological. there's just fertile ground to be discovered. So many things many different idealized settings in learning theory, which have non-trivial feature learning phenomena. I think Jamie Simon will give a talk about this later this week, so I won't dive too deeply into this. Also, many opportunities in the theory of data. There's various different data models which are reflective of different properties that we expect in natural data, not just sparsity. And we also believe that this can go, like formal synthetic models are used in the field right now as toy cases, but we really believe in the development of a field where these theoretical data can actually make falsifiable predictions on natural data, and that there can be iteration on this, and that this can then further inspire novel tool development. And there's just a much wider surface area for mechanistic interpretability than there has been in the past. We're not just necessarily concerned with reverse engineering neural networks. We know maybe the premises are onto something and this is just doomed. But there's we can make them interpretable by design for different ways, either by designing novel architectures or by steering the training algorithms that we use to train them. And so path forward for this research collaboration is piecing together the elephant. So we're currently putting together a research agenda that can really guide this collaboration. I have an HTML document that's supposed to, that's going to be a website soon, but unfortunately I wasn't able to get it on this computer before this presentation. But we really want you guys to help us construct this research agenda. And here are some ways to participate. What's not on here, but be here is really great. We have an amazing lineup of speakers. Couldn't be more excited to have them, and just being here is really awesome. If you want to do more, you can help us define the agenda. If you're on the job market, we're hiring. We'll soon be hiring, and as well as the other organizations within our network will be hiring. If you want to start an organization yourself or hire postdocs if you're an academic institution, talk to us. We can help you get funding. And we also run different research fellowships, which we would love to have more mentors for working in this particular agenda. And tell your friends about us. That's it. Cool. Any questions? Once, twice, thrice? Okay, cool. Thank you so much. Thanks.